Everyone, I'm happy that we are now in more peaceful times. Hopefully it will continue. So today we are going to continue discussing the Laplace equation, and later we're going to discuss a little bit the Poisson equation using two methods. One of them is called the green function method, and a related method called the image method. This is a rather technical lesson, to put it this way, because we are trying to teach you how to solve equations using boundary conditions and things like that. There's a lot of math, but this is the type of math that you need in your exercises to solve real problems, more or less real problems. So I hope you still enjoy it. The lesson today is not so much based on Griffiths. This is a little bit beyond Griffiths. So up to now I really followed Griffiths very carefully, but now we are slightly extending it. So in the previous class we studied the Laplace equation with spherical symmetries. We had the YLMs in the homework, we had Legendre polynomial solutions, expansions, and now today we are going to begin with doing something similar, but we're going to use the cylindrical coordinate system, and we are going to teach you a method of how to solve very general problems with cylindrical symmetry. Actually, the same method can apply for other types of symmetries like Cartesian symmetry or spherical symmetry. If you go to the exam sheet of previous years, you'll find at the end some summaries where we have certain table or tables which help you solve all kinds of equations. So the main part here will be, I'll give you some table. I'll soon explain what I mean. And with this table, if you understand this table, you can solve all kinds of problems quite easily. Read out the table. So I'm going to teach you how to do that. So let us start and think what exactly are the problems we are considering in cylindrical symmetry. For example, we have some cylinder which looks like that. Oops, very bad drawing. And then we are solving the Laplace equation. So the Laplacian of the potential V is 0. We are usually looking inside this object. And on this object we have boundary conditions. For example, let's say here the potential is a constant, and let's say here it's 0, and down here it's also 0. And we can have all kinds of combinations of such a situation. So what makes the problem not trivial is, of course, these boundary conditions. And the question is simple: how do we solve this type of problem? Where obviously the problem, the geometry, implies that we have cylindrical coordinates, symmetry. So another example will be two cylinders. One inside the other. So first of all, because the system is finite, the solution is not so trivial. So there is a difference between finite systems and infinite systems, and you need to somehow know what will happen when I take the system to infinity, and this influences things like the orthogonality relations that you're going to use later. So there are many subtleties, different types of things. Now, you saw, for example, if this would be an infinite cylinder inside the cylinder, and if you add the charge inside, then this is a very typical problem in high school where you solve it with Gauss laws. You exploit the symmetry. But here I don't talk about I don't talk about the charge. I talk about maybe on this cylinder we have some V, and this one is grounded, so this is 0. So we are solving Laplace and not a charge problem, at least at the beginning. Okay, so we need to use cylindrical coordinates. This is just by symmetry, and let us remind ourselves what these are. So in cylindrical coordinates we have three coordinates which are r, phi, and z. And if I use the usual Cartesian coordinates, I'm not going to write x, y, z. So phi describes the angle of rotation along the z-axis. The z coordinate is obviously in the z direction, and the r is just how far you are from the z-axis. So these are the three coordinates, r, phi, and z. And we want to solve the Laplace equation. And if we have the Laplace equation, what does it mean? We have the Laplacian. So let us write the Laplacian. Okay, generally speaking, it's this Laplacian operator on this potential V. And this is given by this object, 1 over r, d over dr, r, d over dr, v. So you see here, I have r, dr, so this has no units. So this object has units of 1 over meter squared. So this is, of course, at least correct units. And then you have plus 1 over r squared d squared d phi. So phi has no units. This is 1 over meter squared. And then you can guess it more or less from the Cartesian coordinates. You have the derivative with respect to z. And all this is equal to 0. So this is the equation. And how do we solve this equation? So this is the method that you already know, and we also discussed here when you discuss in different courses like quantum mechanics. Well, maybe not in quantum mechanics because of the war. Did you learn problems in quantum mechanics in 3 dimensions? Yeah?
We just stopped quantum mechanics.
In quantum mechanics, you say yes, you say just start.
Yes,
Or
okay.
maybe it's not a contradiction, but okay. Let us assume that you saw something similar in somewhere else. So the method we solve these type of problems, in quantum mechanics, this Laplacian is representing the kinetic energy. It's a bit more complicated there, maybe. But the usual method is the method of separation of variables. So we have an ansatz. The ansatz says that the v of these 3 coordinates is going to be written as some function capital R of R, some function phi of phi, and I don't have too many letters in the alphabet, so I'll call it z bar of z. Now, this is a very unique solution, one of solution out of many solutions. We'll have all kinds of quantum numbers, quantum quote unquote, all kinds of discrete variables inside. And of course, eventually what we mean that this general solution, you will describe it as a linear combination of all these functions. And then depending on the boundary, you'll choose specific coefficients, etc. You need to go through all this machinery of solving these type of equations. And that's actually the difficult part. This is the reminder part. So we can put this equation inside here. And for example, if you look here, I'll take the derivative. So here I'll have the second derivative of this big function z. Then I'll divide it by this. And then I'll have here a function which is a function of z only, while the other guys will depend on r and phi. And if that is correct, then this part has to be a constant, and this part has to be a constant. Again, I'm reminding you, if you don't remember, please ask ChatGPT, and it will explain it to you in 2 seconds. So by doing this separation of variables, again, we get 3 equations. Why do we get 3 equations? Because we are living in a dimension equal 3, and we have 3 functions. And these 3 equations, I'm going to give them. Let us start with the easy ones for z. So this is the second derivative of z. This is the second derivative here. This is equal to some wave vector, we can call it, kz.
Wait,
Z.
the R shouldn't be before the second derivative of not this R, the later R. Like it shouldn't be
Here?
here. Yeah.
I don't think so, but please check. I'm pretty sure that not. So we have this type of equation, which is a familiar equation for you, I think, because this is, you saw it many times. It's like a spring constant thing. I'm not saying what is kz. Kz is some number at this stage. And depending on the boundary, it can be either quantized or continuous function. Continuous or not. In finite domains, usually this guy will be quantized. In an infinite domain, it can be a continuous function. Again, like in quantum mechanics, where you have a wave vector in free space, it can be k, and a particle in the box, it's quantized. It's the same thing. So this is this equation, and we know how to solve it. I'm not saying that kz is complex or not, so this can be negative actually, or positive. And that will depend on what are the boundary conditions eventually. So how to choose this kz is actually the trick. That's the subtle point here, how to choose it as positive, as kz squared, positive or negative. But this is a very simple equation. We know how to solve it. And this is one quantum number. And then you have another simple equation for the phi, because it's the similar, you multiply by here. So the second derivative of phi is some k of phi squared. And we choose a minus. The choice of minus is not so important. It's just a convention, because again, this k phi in principle could be either giving you a negative or a positive. So we choose the minus because soon you'll see that in most problems, this k phi squared is positive phi. So these two equations are as easy as you can get. And we have here two quantum numbers. The difference is that this kz has units, 1 over meter squared. This k phi has no units. It's some number, right? Because phi has no units. So there is a difference between them, and soon we will find these guys out. We know how to solve these things. These are these trigonometric functions or hypertrigonometric cosine. Okay, this is all well known. And then there is another equation which is also pretty famous. And this is this equation when after I separate variables r ddr r dr r. So when I take the derivative here, I get the k phi here, right? So here I get kz squared r squared. This is actually from here. And minus k phi squared. This is multiplied by capital R. All this is equal to 0. Now, this equation, luckily, our friends the mathematicians solved it, and this is essentially the Bessel equation. So this is the solutions here are going to be Bessel equation, Bessel solutions. So again, we know that here we get trigonometric or hypertrigonometric function. Here we get Bessel functions. But there are 4 Bessel functions. So it's a big mess. How do you navigate in all this mess? That's the question. How do you choose the different type of Bessel functions? What are these Bessel functions? Again, depends on the boundary. That's the problem, and that's what I'm trying to help you kind of figure out. So let us start with the simplest thing, and that is the simplest thing would be actually with the phi. So assume that all the angles phi are accessible. If you remember the previous lesson, what did we discuss? We discussed this problem of a cone on top of a plane, and then we had this problem that in some domain you could not access everything. So what is not accessible problem is maybe you have a pizza pie on top, something like that. You are walking inside, then the phi is not accessible because in this region you're outside. So I'm not going to talk about this because we solved such a problem with spherical coordinates when we talked about this thing. And then what happens, you get some strange new functions which are not the typical functions. But I'm going to talk about the typical, at least with respect to phi. And what does this mean? It means that you have, when I look at these type of problems, then if I go from phi and I go on a rotation and I come back here, the solution comes back on itself. And there is no question about that, which means that we are using phi plus 2 pi equal phi. Now, what does it mean with respect to this equation? You might say, okay, this equation can decay or explode exponentially, right? If this would be if this would be imaginary, then this would be positive. Exponential functions going up or down would be a solution, but they do not satisfy this. So if you don't have this pizza shape, if you have this round shape, what does it mean? From respect to phi, no exponential functions, just trigonometric functions. And these trigonometric functions are going to be trivial. This phi has to be, I'll write it symbolically more or less, EIL phi. It could be plus or minus. Because you see immediately here, you solve this equation. And what is this L? This L is actually this K. Because you see the second derivative will give you L squared. Here it is. And why does it have to be L? Well, because of this. Because you go back and you return, and then L has to be an integer. L equals 0, 1, and 2, etc. So L is a non-negative. L is going to be a non-negative integer. So this aspect is quantized in the sense that this L is because of the periodicity of the condition. This L is this quantum number is always quantized. What about the second one? Will it be also quantized? That will depend if the z direction is finite or infinite.
If it's infinite, like it's just a polar.
Then it will be a continuum.
Because it's symmetry.
It's not exactly because of symmetry. We'll still have cylindrical symmetry.
No, you have.
We don't. You said spherical, I think, but maybe I didn't get you. But it's simply related to the fact that when this goes to infinity, the boundary condition is at infinity, and then all the quantum numbers form a very continuous, nearly continuous, as you increase the size of this thing. So I don't see it as an issue of symmetry. I see it an issue of the size of the system, of the scale. Okay, so what we wrote here is actually k phi equal L, and that's it. Okay, so now what we can do is, now this equation I already solved. I mean, I'm going to write it down soon, but this equation is either trigonometric or hypertrigonometric functions. So we can also wipe it out. I'll soon write it down. But there is no simple way or general way to say something general at this stage at least. And now we want to treat the Bessel function. So first of all, we define some coordinate x r. So this is just to make this equation a little bit more conventional, because you simply see here I have kz r squared. Let's call this all this junk x squared. X is dimensionless while k and r have units. So this is just a simplification. And then the Bessel equation for what? For capital R. Remember, that was the radial component, this component. The Bessel equation becomes very simple. It's the same thing. You can read it. You know, this R goes into X. Simply think about kz equal 1, and then you just change it here. Simple change of variables. D over dx, x, d over dx, r, plus or minus x squared minus L squared. So this is this chi phi. All this times R equals 0. And here the new thing is that I introduced this plus or minus. So this is the new thing here, which you didn't see here, because kz, as I mentioned before, it can be either positive, kz squared can be either positive or negative, and this corresponds to either plus or minus. So if it is kz plus is plus, you have a plus. If kz squared is minus, it's minus. Of course, the more interesting question is, how do you know, is it plus or minus? That is exactly the question. What is it? So we just give here all the options, and later we have to choose a plus or a minus. Depending on what? As I said before, on the boundary conditions. Okay? So we will need to choose this. So the plus sign, this just means kz squared positive, and vice versa. If the minus sign kz squared is negative, and that means, if you think about it a little bit, that either your solutions are trigonometric or hypertrigonometric. Okay, so we treated this, and now we have to look. Okay, there is this equation. I don't expect you to be experts on Bessel functions, but okay, we go to ChatGPT, whatever, and we look out what are the solutions, and we first of all write them down. Let us try to be a little bit tidy, and we have to summarize all our options. So the Bessel functions again come from this, this solution, from this equation. I just look them up in some book. Now I can build a table of, it's not a solution yet, it's just of possible solutions. It's a kind of wide, very wide description where many possibilities are present. So let us write down this magic table. I took it from Nadav Shnerb's book. I like this table. So we will write down the table. And what do we have in this table? We have the function r. We have the function. We have the function z, which is of the z direction. R is of the r direction, and we have another function, which was phi, right? These are the options. And we have here two options. One of them I'm going to call Aleph. Another option I'm going to call Bet. What is Aleph and what is Bet? So this is kz squared greater than 0, which corresponds to the plus case. And this is the minus case, kz minus. So we have 3 functions, and we have 2 options. Altogether we have 6 domains here. So we mentioned already that the z and the phi are the simple ones. And the other one is, so here I'll have Bessel functions. Here I have trigonometric and hypertrigonometric function, and what will I have here? Just trigonometric function, because I said already that the solutions of the phi direction is just trigonometric and not hyperbolic functions. Okay, so let us start with the easy ones. So we said already you have some coefficient, which is, I'm going to write it with sine functions. You can write it with exponentials, complex exponentials, plus f cosine L phi. This is what we said already before. L is the solution of this simple equation for the phi. We have this L squared down here. Remember that? No, it's not here. But this is the L squared, and L is again integer quantized because of this thing. So this is the sign. We don't have anything decaying, and what do we have here? We have the same thing Exactly. What is the z direction? What is e and what is f? These are some coefficients, because remember, the equation is linear because Laplacian of v is equal to 0. So you can multiply it by any constant, you can get some constant. Eventually we need to determine all these constants. When we put them together, usually it's not so many constants, but there are some constants. Okay, here what do we have? We have, in this case, sine kz. Again, what is k? K, I'm going to now use the notation that k is simply kz absolute value. I'm just taking out this subscript z. So this is the same thing that we had here, but with absolute value, because now I distinguish between the plus and the minus. So here I have cd cosine kz. And again, this is trivial because the equation for z was take the second derivative and take out twice k, and then you get with the minus sign, you get the solution. And what is the other solution? If kz would be negative, so it will be here c sine kz plus d cos kz. What do I need to add here? H. So, but this is not h bar from quantum mechanics, this is just h. So these are just the hypergeometric functions, and they replace and they describe the fact that kz is less than 0, and then you can have solutions that explode or decay exponentially, that's all. Okay, so here we had two functions. Here we had two functions. How many functions we'll have here? We'll also have two, but these are the Bessel functions already. And these are given by the following, some coefficients, JL, KR, again, this quantum number that appears both here and here, plus B, Y, L, KR. And here I have A, I, L, KR, plus B, K, L, KR. I admit that K is not a good name, but this is how the Bessel functions are called. So these functions, J, Y, I, and K, are called Bessel functions. The first two are Bessel functions of the first kind. These are modified Bessel functions. You have tables, how they behave at large distances, short distances, series expansions. All of them are solutions of this basic Bessel equation with the appropriate sign. Now, how they behave is actually important. Now, again, if you go to an exam, you'll have a table with all these functions, how they behave at different limits. And this is important. And why is it important? Because we need them. Usually what we need is the asymptotic solutions of these functions. Why do you need the asymptotic only, not the whole function? The reason is because usually you have the boundary condition. And the boundary condition will be determined by the asymptotic of this function, not by the whole function. So if you know something on the boundary can be on the origin, sometimes at far distances or finite distances, then you can choose this number. And what is the goal of different exercises? What is the first goal is to say which one is the correct solution, this one or this one? And then can we say something trivial on these things? On these, what I mean by trivial, I mean, can we say, let's say, b is equal to 0? Then we throw away these type of Bessel functions. Or can we say, I don't know, c is equal to 0, etc. And this is very complicated, or it's at least at the beginning it's complicated because this depends on all the boundaries, and you need to know how to choose, what to do with this horrible mess. But okay, this is our main tool, and soon we'll use it. So now we need to look a little bit how these Bessel functions look like. because then eventually you will like to solve them, to use them. So how do they look like? Some of them. I'm not going to give all the properties. We can have a full course on Bessel functions. But one of the famous Bessel functions is actually L equals 0, and we will soon see what type of problems are like this. But let us start with this JL of some x. X is just some variable. This is math. So it starts with 1. And it behaves something like this. It oscillates. So this function decays plus oscillates. Maybe oscillation is not so surprising. Also, the sine function is oscillating. The cosine function is oscillating, which you add when you add Cartesian coordinates. And remember this, you have a boundary on the cylinder. Okay, so you'll have some oscillations like you have, like in a particle in a box, but now these are with an additional decays. So eventually this goes to 0. If I remember correctly, it goes like 1 over square root of x to 0. It goes slowly, but again, these are details which are important, but not so important for us. What is important for us? That it starts from 1. This is actually important. Another thing is that it has these zeros. So these are the zeros of the Bessel function. And this first 0, we are going to denote by Z10. What is Z10? What is the number, do you know? Does anyone know? Did someone teach you about these zeros? Yes? Oh, it teaches everything. Okay, so we have this Z10, that's the first 0 of the index 0 is of the Bessel function. So this in general will be, this index will be for L. But now we are dealing with the 0, the Bessel function, and this is the first. So this is Z10. What is this guy going to be called? This is going to be called Z20, and this guy is going to be n equals 3, etc. There are many of them. And you can write a program and you can find them somewhere on the internet. And they are known that, for example, this guy is equal to 2.40 something, if I remember correctly, 2. Now, how come I care about these zeros? Can anyone say, well, why do we care about them? What type of problems should we care about them? So remember, what is this solution? Let's say that all the rest are zeros. So you have many problems, or typical problems, not all of them, but some of them, or problems that we can ask students because then you can solve them. Let's put it that way. Where on the boundary, this is the boundary with respect to R, the potential is 0. And then you care about the 0, you kind of quantize this thing like zeros. Where did it? This appeared in a very similar way in many other courses, in Cartesian coordinates. What is it similar to? Let's say you have a standing wave between two zeros with a sign k. So k had to be quantized, right? So the choice of k was similar to a kind of knowledge of when does the function become 0 on two boundaries, right? And again, here we will exploit, I'll soon show you exactly how, this 0, that 0, in order to quantize now for the Bessel function. This was very rough, now soon will come some examples, but I just wanted to explain where we are heading to. Now, how do the other functions JL behave? More complicated. So this is the function. This is L equals 0. The other functions, the one property of them is that they all start at 0. So JL might look something like that. Oh, very bad but it doesn't matter. JL XL greater than 0. They all start from 0. So my point is JL x equals 0 is equal 0 for L bigger than 0. This implies that J0 is a special one compared to the other guys from a mathematical point of view. Now we need to add important tool. What is one of the most important tools is the orthogonality, which we will again use later, but actually there are several orthogonality relations, one of them, and in these problems one of the tricks is when we use orthogonality, when do we use orthogonality relations is that, okay, we have some boundary conditions, we expand in all these things, and then you use orthogonality. Sometimes you need to use orthogonality with respect to the sine functions, and in other cases you need to use orthogonality with respect to the Bessel functions. When this case and when that case, you need to know, that depends on the problem on the boundary condition. Again, this is a complication that you need to be aware of, and you need to train yourself in exercises, which is the correct orthogonality relation to be used. And this is something you need to think about it for a specific problem. But one of the possible orthogonality relations out of many, because again, you have for the sine, you have for the Bessel functions, and you have for the y's, and you have for the i's, blah, blah. One of them is, now I'm focusing only on the j, is this beautiful equation that you don't need to remember, of course. So A is like an integration. I'm now integrating over these j's only. This is like a radius of the system, some A, some distance. R, J, L, Z, N, L, R over A, J, L, Z, M, L, R over A, dr equal JL plus 1. So you go from L, you go to L plus 1. Zn L absolute value squared delta Mn. The delta Mn, as usual, is the Kronecker delta, but notice what are these indexes related to. These indexes are related to the zeros. This is M and this is N. So you need to look at the zero, let's say the first zero, then N is equal 1, or the second zero, this is M equal 2. And the orthogonality is with respect to these two numbers. Don't be confused with the L. The L here is fixed, here L, here L, and then you have here this number. So with this thing you can, as I will show you soon, you can normalize things. Now this is valid usually in problems where the system is finite. This is the size A, is the size of the system, the size of the cylinder. When it's infinite, you get a different type of equation. You take you cannot actually take it to infinity easy. So this is a kind of orthogonality relations that you need to use. So now, okay, this was a little bit about this J. Now, how does and you need, again, in your toolbox, you need many of these orthogonality relations to actually solve problems. How does the Y function? So again, the J goes into Y. These are called just Bessel function of first kind. These I and these K is actually a linear combination of the first one with plus and minus indexes. I'm not going into the details, but the Y, how does the Y behave? So we said that roughly speaking, this J is oscillating and decaying, these y's are also oscillating and decaying. It's like you see here, you have a sine and a cosine, so this is oscillating, this is oscillating, this is decaying, so they come together. This is different from these functions that have a different behavior with no oscillations. So this YL is something like that. This is for y0. This is a function of x. And this one is going to be, let's say, y1. Don't be confused with YLMs. This is just y of the Bessel function. So the main important part here is going to be this diverge here. Plus oscillations. Plus eventual decay of these oscillations. This is going to be enough for us that in many cases, so we can immediately understand what's going to go on. Let's say we have a problem with this sum cylindrical. Let's say we are in this branch. Can we have a solution which is of the type y for the Laplace equation? Usually, unless something very strange is going to happen, the answer is no. Because the minimum of the, remember what I told you about the Laplace equation, the minimum of the potential has to be on the boundary, right? So if it goes to minus infinity, then these, the minimum will be on r equals 0. Yeah, r equals 0 correspond to this x equals 0. So immediately it's not, I hope you don't shut yourself completely to these functions, but these functions are, let's say, more rare in most problems. Of course, that is the problems that we like to give you in exams, but that is a different story.
So this is only for problems that don't include the 0 point.
For example, yeah, that could be a very good example where you don't have the 0 point and then you don't have the divergence. Like the two cylinders, I had one inside the other, it doesn't have, if you walk between them.
Is there any other examples? Or this
No,
is the one?
as far as I know, yeah, these are the examples where you are, the origin is excluded. We had something similar also with spherical problems when we had this r to the power l plus 1 and r to the minus l. Then we had inside and outside the sphere. So you don't need two cylindricals. You can look at the solution outside the cylinder. One cylinder and then you're looking outside. So it's very similar to what, it's very similar yet different. The difference is these oscillations that, while in the spherical coordinates it was 1 over r to the power l minus l or l plus 1 and things like that, right? Well, it's a bit similar but still different. So
about the Neumann function that is not, how did you say it is not common? You said the Neumann function is not common?
I said this function, when you have an access to the origin, is not common. That was the more precise statement. I'm not saying it's impossible. In that case, because again, you don't want a solution that diverges here. That's all. So you need to exclude to use it, you need something more complicated. Okay, so then we're going to have these j's. Let's write, and then we have these other functions that, again, series expansions. So this is the I, L. So again, L equals 0 is special, like JL equals 0 is special, and it starts at 1, and the other guys start at 0. So this is IL greater than 0, and they explode exponentially for large x. If you want, like, Koch explodes exponentially, and now there's no oscillations.
Unless you have an infinite.
No, this is not related to the potential. This is just a property of the function. So KL, so again, IL, this is the value at x equals 0. It's 1. The other guys are starting with 0. The other guys go like x to the power L, as far as I remember. Or all of them go to x to the power L, and x to the power 0 is 1. So the KLs, they diverge on the origin. There's something like that. So they diverge, all of them, on the origin. And you have no oscillations, like these two. So to summarize, these guys have oscillations, these don't have oscillations, maybe similar to sine and sine hyperbole. But the oscillations are not so simple because they are not periodic functions, right? The zeros are not periodic, so that makes them more complicated. And in addition to the oscillation, you have decay. So it's a bit more complicated than a simple sine function or cosine function. Okay, so after all this long introduction, now we can solve problems, some of them at least, quite easily. And so we have, this is now an example, a cylinder with radius A, and height h. Potential on the lids, I'll assume is 0, and on the surrounding, otherwise it is V, some constant V. So what do we have here? We have here a system. The lids are the top and the bottom, that's what I mean by lids. The size, the height here is h. The radius is a, so this distance is 2a. So we have a radius here, 2 length scales to this problem. Potential on the lid is 0, so 0 here. This is the potential itself. And on this wall, the potential is V. This is the boundary condition, and we are looking inside, and then we are asking, okay, there is a Laplace equation, and then how to use this table, and then how to find the coefficients. That's the general type of questions that we have here. And I claim that by looking at these in this table, we can easily, more or less easily, after some practice, it's not so trivial maybe, we can find a solution. And this is the whole issue of this kind of exercise. So let us see how you can do this. I mean, the way to do this is we want to either choose, is it a plus or minus, and what happens here? So how can you do it? First of all, let's plot it here, this example here. How would you start? Or okay, I'll tell you how I start. You always want to start with the simplest thing, and maybe the simplest thing here is the phi. Why is it simple? So let's say that I go here in the problem and I rotate, not a full rotation, but with some angle. Is there a difference in the potential if you are here or you're rotated by, let's say, 45 degrees? The answer is no, because of the boundary conditions. Remember, they are a constant on the boundary and 0 on top. So what's the difference what phi you are? So the solution is independent of phi. So immediately we understand from symmetry the solution is phi independent. But what does it mean that the solution is phi independent? What does it mean?
For every phi, the potential is
No, don't repeat. I said it just now. What does it mean? What's the consequence of this in this table?
L equals 0.
That L is equal 0. So this means that L is equal 0.
Why?
Because then, if L is equal 0, then cosine 0 is a constant, and sine is going away. And that means that there's no phi dependence. If you take L equal 1 or 22, you will have a phi dependence, and that's not allowed. So we manage quite easily to say what is L. And that's very good because we had here an infinite number of L's and now we have only one. Okay, this is a very simple problem, that's why we could do this. In general, it will not be so simple. So now let us look at the lids. So we have a lid and a lid. So I'm looking now in the z direction. Why am I looking in the z direction? I'm going to look here on these solutions. I already said everything about this guy. So on this solution, we have potential V equals 0 and potential V equals 0. That's the boundary condition. What can we say about this function z? Can we have this sinh plus cosh?
No.
No, because these functions are not going to 0. There are some constants. You cannot make them 0 on both the top and the bottom. So it means, first of all, no cosh sinh solutions. I mean here for z. And it also means if there are no cosh, then what we have here, the solution is of the type A, type Aleph. Solution is plus Aleph. So what did I do up to now? I can throw away this whole solution. I don't need these modified Bessel functions, which are not so famous. I can work up here. That's great. And also these functions are gone. I know what is the L. I already made some progress. What can we say now? Now we go to the less familiar functions, which are these Bessel functions. And now we have to say something. What can we say? I think it's not so difficult given the given this. Given this graph, this YL, okay, it's Y0. This is the Y0. It's Y0 because L is equal to 0, but what happens to Y0? It diverges on the origin. Is this allowed for Laplace? No maximum, no minimum, no extremum inside the domain. I taught you that, looks like years ago. So what we know now is Y0. I write 0 because L is equal to 0. This diverges. Where is the diverges? I mean, diverges are what I mean by that on R equals 0, in the middle of the cylinder. Diverges. This is impossible by the properties of Laplace equation. No extremum. So what does it mean? It means we have only J0 type of solution, KR. Now, what is left? What is the next step? It's also a simple step. What is the next step? What don't we know? We already said know this, only J0. This is gone. What don't we know?
Coefficients.
Coefficients comes at the very end, before the coefficients. K. We don't know what is K. But this is simple because it comes from here. So now we look what is K. And how is this done? K, remember, this comes from the Z direction, so I can look at these two lids. And what is the solution? So first of all, remember the geometry. I define this as Z equals 0, and this is Z equal H. So the last thing is that V at Z equal H and V at Z equals 0. Okay, this is equal 0. So what does this mean? Again, you had this many times in different courses. What does it mean on this function cos? the function cost is not 0, but d has to be 0, but it's the same thing. Yes, you're right. So immediately we know we need to choose d equals 0. In that sense, you were right. We are choosing some of the coefficients, but not all of them. Okay, so maybe that's what you meant. D is equal 0 because I don't like cos k. In the z direction, it does not satisfy the boundary condition. And then we have the sine k of z, but not every sine, okay. Sine k of 0 is of course 0, but sine k of h is not generally 0. Here we get the zeros of the sine function, similar to the zeros of the Bessel function that I did not use in this problem. So in this problem, there's no zeros of the Bessel function, so you need to wait a bit for those. So what do we know? We know that sine kh, that has to be equal 0. H again is a length scale, the size of the box, of the cylinder. Okay, so that just means that k, it's what we called before kz. Just to emphasize that the quantization comes from the z point of view, is n pi over h. Why? Because again, if I'll put here n pi h and put z equal h, that will give you 0 on the boundary. So here we found the second quantum number, and it is also quantized. The other one was so trivial that we had only one quantum number, L equals 0. So this is essentially the solution. And now we are done, more or less. Before finding all the coefficients, that's okay. We can have a kind of break. So now we can summarize all this. Summary. We have V Wait, did I mess up?
Supposed to be modified Bessel function.
Where did I mess up? I messed up. I made a mess up. I messed up badly. Yeah, I messed up terribly badly. Sorry for this. This is a very bad mistake. I made a mistake. I made a very bad mistake. Sorry about this. Which means we are at this one. Sorry. Summary. Go backwards. Replace J actually with I. I made a mistake, but it is I of 0. This was not a mistake. And this is case B. I don't know why I made this silly mistake. So the H is here. Replace J with L. Sorry again, I really apologize. So the final solution, if I do this correction, and I'll just write it down and then I'll summarize, is the following. V, R, phi, and Z. This is sum over some coefficients an, these coefficients, of the function I. The reason why nothing has changed, we see this I, 0 is 1, and the other guys are 0. So, I mean, this Y, only the I, like the J 0, now it's the I 0, only coming in. N pi R over H. So what is this n pi r over h? This is simply this k that we found here, n pi r over h, so I just plug this one here. And then I multiply this by the sine function, n pi z over h. So again, all this junk, this is the k. This is what we had here, the k, this is this k. This function is the sine, so this is the sine. We choose only the L equals 0. The function k, I said it before wrongly, but the function k is disqualified. I said y is disqualified, but k is disqualified because you see here it diverges. So everything was right, I just replaced I and j. Okay, sorry again. So this is essentially the solution. Now we need to find these ANs. And now we need to make a decision how to find them. And how do we find them? So these functions I, they are just increasing exponentially. They actually, the orthogonality is made with respect to, you're going to use the orthogonality of sine functions. This is something you know because you just multiply by a sine. These are like Fourier series. You integrate over z from 0 to infinity, from 0 to h, and you are done. So I'm not going to do this. Essentially what you do, so here you don't need some very special orthogonality relation. You use the usual orthogonality relation to find z. And what does it mean in practice? What do you need to do is v at r equal a. What is vr equal a? Oh, remember what we had here was a cylindrical, it's just a constant, right? It's some number that you fix, that's all. Then I can just plug here r equal a. So all this junk, I'm going to write sum over n, bn, sum bn, sine n pi z over h. So somehow this infinite series has to be independent of z. This is given by these coefficients. What are these coefficients? These bn's are simply an, I, 0, n pi on the boundary h. This is just a definition of these numbers. And then you use the orthogonality relation of the sines. You multiply it, you integrate over z from 0 to h. You filter out some numbers like bm, and then you get this bm's. You get all these numbers. If you get the bn's, you can get the an's, and then you are done. So this is a simple exercise, and then, or a well-known exercise, and then you can write down the full solution like this, 4v. You need to use normalization and all kinds of things like that. Sum over n, but only about the odd ones. So n equal 1, 3, 5, etc. And 1 over n, I0, n pi r over h, I0, n pi a over h, sine n pi z over h. You can rather easily see again the main features. The solution is 0 on z equal h and 0 on top because all these coefficients go away. The solution does not depend on phi. That's why we have here the L equals 0. Here we have the quantization, which is because of the quantization in the z direction. And then you can ask, okay, what does this mean? It's not such a nice solution in my opinion. So what you could do, for example, to check that you didn't make a mistake in this calculation, at least this is what I did, is the following. You can go back and you can say, okay, let's put here r equal a, and then this sum, 1 over n, this sign has to give you pi over 4. So this sum, independent of what is z and the h, when this guy is taken to be 1, has to be pi over 4. And you can check it, and of course, I mean, you put it into chat, and you can check. This is just a sanity check that it works. Of course, the units are correct because this is the v. And of course, you can also just plug it into the equation and see that it works. That's a different method of solution. So this is the solution. Now we want to, so this is actually a very simple solution because we didn't have any zeros or Bessel functions. So let us go to a different equation, a different scenario, where these zeros will appear, and then, okay, and then we'll have the j. I was going back, so this will appear in different boundary condition. So let us look at the problem where, so this is problem 2. On top here we have v, some number, and all the rest is 0. Again, the height of this cylinder is h, capital H. The radius of is a. And now we are dealing with this. So now we are already expert. What happens with L equals 0? Now we can do it a bit faster. L equals 0 because there's no phi dependence. Okay, no phi dependence. L equals 0. The solution has to be finite. The solution has to be finite at so now we have to have a solution which is finite on r equals 0, but is 0 at r equal a. How can that be? How can it be 0 at r equal a? This is not the functions that go up exponentially, the y's, I mean. It's not the function that go up. It has to be the functions that oscillate because those have the zeros. So by remembering a little bit about these functions j and y, we can say, okay, there's no y here. There is only j, and we are left with only j0. Why? Because the other function here, so this function will diverge, like here, not good. But then you can say, oh, maybe it's one of these functions because they also oscillated. But remember, the one that oscillated, I have it here. These functions don't oscillate, right? They do not oscillate. This was previously, so it must be here. That's the main point, actually. So now we are in case A because we need oscillations. Again, why do we need oscillations? Because we want this function to be 0 when we go outward in R. And functions that are not like that will not. So this helped us solve this branch and kill this one and now we are with the sine hyperbole and cosine hyperbole. Now, remember, before I said this guy has to go away because we only had the sine, because it was 0 on the bottom and on the top. And now it's something on the top and some 0. And that's why these sine, sinh, and cosh are admissible. They are kosher. Yeah.
Why can't we use the IL, if we use IL equals 0? I mean, we can't create a linear combination of IL of I0 and I1 that is both non-zero.
There's no, first of all, there's no 1. This I said at the beginning, L equals 0 because there's no phi dependence. So we are left only with 0. And then there are no linear combinations because there's only L equals 0. Okay?
Oh, okay.
So it was very important to filter out the symmetry here, L equals 0, and then you're done. Okay, good question. So you understood this question. He says, okay, maybe you can have linear combinations of diverging solutions. One of them will be a plus, one of them will be a minus, and then you will wipe out the divergence. You're a mathematician, I think. No?
Actually, I'm a computer scientist.
Okay, it's even worse. Okay, no, fine. Not a problem. So, yeah, but we are choosing here L equals 0 in a physics course. Okay, so we have only this J0. So what is the solution? The solution now reads V, R, phi, and Z, sum of ran, some fn's. I don't know why I choose fn's, but it doesn't matter. J, we said only 0 because L is equal to 0. Zn 0 R divided by A, sinh, and I'll soon explain. I'm using all the time the table. I'm using it, and I'm not going into all the details, but some of the details. This is the solution, and let me explain. So why is it the sinh? Well, it's on this branch, but why is it not the cosh? It's not the cosh because at z equals 0, the solution is 0, right? Down here. So this is why I choose the sinh and not the cosh. I just look at the table. Okay, I don't make mistakes, then I choose the sinh. This is 0 at z equals 0. This again, this is the Bessel function, it's oscillating, and here you see, this is the important, maybe one of the important issues. I introduced these Zn zeros. Those are the zeros of the Bessel functions that we had before. Now you see why I mentioned it at the beginning of the class. Let's put here R equal A. Remember, R equal A, we are here on the boundary. So we have A over A, and we have J0 of Zn 0. What is J Zn 0? By definition, it's 0, right? Because that's the 0 of the Bessel function. So here enters these zeros, these strange numbers. Remember, the first one was 2.402. The other one was another strange number, etc., all tabulated, but we know them. And you see that the solution here is 0 on R equal A. And again, the summation, what is the summation? This is a bit maybe weird, or maybe it's obvious, I don't know. The summation is over zeros of Bessel function. I mean, the index n is just going 1, 2, 3, but the meaning of it is I'm summing over all these Bessel functions that I can find in some book or somewhere. Now we need to find Fn. Now we need to decide, we have here two functions. Which one of them I'm going to use the orthogonality relation? Is there a orthogonality relation to the sinh? Do you know it? Well, maybe you're not sure, maybe you think it exists, but I don't know it. So it most likely has to be with the J0. And this is the orthogonality relation I gave you already, right? Remember this orthogonality relation that was for L, but now L is equal to 0, J0 multiplied by J0 times dr. You integrate, you get what will you get when you multiply it by J0? You'll get the J1. It jumps from L to L plus 1. This orthogonality relation will determine what is Fn. I'm not solving what is Fn. You can solve it by yourself using this orthogonality relation, but this is the structure of the solution. And just to summarize, my point is that if you have this table and you understand it, you can, in my opinion, hopefully, easily solve problems with all these considerations coming together. Okay, I hope this is the message. This is the only message of this. Yes.
The weight function of the modified Bessel function is also R?
Here we are J. You mean this ones?
No, when you...
You mean the orthogonality relations?
No, when you project the modified Bessel function, you have the non-modified Bessel function. You include in a...
You mean these functions,
Yeah,
of the first kind?
You include factor of R on the integral.
Yeah, you need to multiply. Yeah,
So
this is like a Jacobian.
Is this the same at the modified Bessel functions?
You mean when you look at the orthogonality relation?
Not the solution, but the integral.
Yeah, inside the integral there is an R. The modified Bessel functions are actually linear combinations of these two guys, one with a plus and one with a minus.
Oh.
As far as I remember, so again, if you go here, I have it, and we can look at it up later. So again, when you go, I'll answer you in two ways. When you go to the exam, you'll have these kind of tables. And you'll have the Bessel function, you'll have the asymptotic expansion, and you'll have all these things. You need to prepare it, maybe previous year prepared it, maybe you can prepare it a little bit better. And you can include all these type of orthogonality relations, some of them are given here. So in this, at least in this, what I remember is about the J and the I, but these are linear combinations of the J's and the I's, and so it's a bit more complicated because when you multiply two things, you'll have sum of two functions multiplied by two functions. You integrate, it will be not exactly the same, but very much related.
Mm-hmm.
Do you understand why? Because let's say the K is a sum of I minus K of alpha. This one. Oops. K of alpha is a sum of this. So this I is related to the complex value of KR, so they are linear combinations. So in short, it's not exactly the same, but similar. Okay, so let us have a break now. And after the break, we're going to start solving actually Poisson equations when we add the charge. So up to now, we just have Laplace. When we add the charge, it's going to be a little bit more complicated, and then we'll hopefully study the image method and the green function method very briefly. Okay, so now we are going to actually continue working with this table, but now we're going to solve the Poisson equation. So up till now we had Laplacian equals 0, and we had no free charges. So now we're going to add charges, and it's a whole new domain of physics. Because, I mean, all these conditions that potential has no extremum is not valid anymore. So let me remind you a little bit. We want to solve the the Poisson equation. So this is the hero of the day. And the most trivial problem is, of course, the Coulomb law. So this is a Coulomb law in disguise. So let us put in the usual coordinate system at point D, and soon you'll see why I want to put here this charge. Then we all know what is the solution from high school, because we know that this is just going to be Coulomb's law, which is Q 4 pi epsilon. And here we have the usual distance, xy squared plus z minus d squared. So x, y, and z are just some coordinates, so we have some observer somewhere in space, and this simply is the distance to the observer, which is on x, y, z, and then this is the potential. This you know, you don't need to come to university for this. So why did I remind you? Because this has to be the solution of this equation. This is also something you know. So by knowing the physics, we know the solution. If I plug this in, I have to get the density, the related density. What is the density in this case? What is the density? It's simply P so you have one charge, it's on place D in the z axis. And that is, if you have a single point charge, that is a delta function. So I did not solve this equation, but I gave you a physical argument why for this potential and this charge density, this has to be the solution. So what did we learn here? We learned that the Laplacian acting on this friend, what will it give you? It will give you the delta function. And this, of course, you can prove mathematically. You can just act with the Laplacian, and we did it, or we mentioned it already. If you add on the Laplacian on this thing, you will get this delta function. But we don't need to prove it mathematically because we know it's true physically. This is my point. Okay, so in this trivial case, we solve the Poisson equation. However, we would like to solve more complicated scenarios. And what I'm going to solve now, and this is why I put it at D, I'm going to solve the case where you have later we will generalize it to more abstract forms, but we want to solve now the case, the following case. We have an infinite surface and we have a charge here on top, and this is the distance D. And this infinite plane is equipotential and has the potential equal 0, so it's grounded. This problem most likely you saw somewhere before. Did you see it? I guess you saw it with Rochman or whatever. So what we are going to do is, first of all, remind you of this problem and try to use it as a starting point for a more general method. I'm starting from an example instead of starting with the general method. But first we're going to also solve it with this type of table. So what is going on here physically? Physically, we have here one charge, Q. But is this actually true? What are the real charges in this problem? Where are they? How can we solve this equation? Here I have just Q and V equals 0. This will, okay, so we all know from high school, they will teach you plus Q, you put minus Q. That is correct. That is called the image method, and we will discuss it and derive it actually, and it will be very useful. So we know the solution of this problem. But I'm not talking about adding here an image charge. I'm asking you about the real physical problem. Where are the charges? What is going on here? You have a real system, there's no image charge. If you go here, you know, when you look in the mirror, you see yourself, you're not on the other side of the mirror. It's not real. You're on the one side only. Okay, so what is happening? That is my question. What are the charges here? What is going on? So does anyone want to say? Yeah.
The charges from the ground move into the conductor and create a field that is identical to what would be created if there was an opposite charge, like
Right.
same charge, same sign, but like in the opposite mirror.
Right. So what we have here is in this plane you have a rearrangement of the charges. That, of course, the total charge of this plane is 0, but how will it go? I'm now going a little bit more into detail of what you said. What we expect here is that in this area, what we will have some charge density which is negative, compensating this plus Q. So here we'll have negative charge, and then it will spread, and of course far away there will be no negative charge. And we can ask the question, what is the total induced charge here in the middle? You can guess what it is. It's going to be the plus Q. So, but now the problem is like this. Here we have this equation. And this equation, people will tell you, to solve it, you need the charge density. But in the real problem, I don't know the charge density. I know this charge density, the delta function, but I don't know what is going on here a priori. So how can I solve this Laplace equation? The equation itself is not really well defined. Now what you could do, you can say, okay, if you want to solve the Poisson equation, you hire some experimentalist and he or she will go and measure the charge density here and find out what it is and then plug it into this equation and then you will solve it. This is not how we do it. So actually, when we do things, we are having a kind of a mixture of the real charges, the charges that we know where they are, and the charges that we have no clue where they are. And this mixture makes this equation not so trivial. What is this rho? The rho is actually all the charges if you know them. But in real problems, you have this equipotential surface, and then we need to use some kind of clever tricks. And the way this is done is we solve it in one domain, and we then apply some boundary condition. So in this domain, there is only one charge. So in this domain, there is only one delta function. Then we apply a special boundary condition on this, and we don't use the charge that is in the surface, at least at the beginning, but rather we eventually deduce it. So let us see how this goes on. And let us say that we do know nothing about the image methods. So the first guy who solved this problem with an image method, you might think is a very smart guy. You think he was a smart guy? Maybe he was very smart, and he guessed the image method, because this is what you are taught. But my opinion, he didn't know about this image method, but he solved it the hard way. What is the hard way? With the table that I just gave you, this table. So let's solve the problem like stupid people, and then see how you find the image method, and then after I find the image method, then I'll tell you, oh, look how clever I am. I'm going to put a charge here and a charge there, and everything is easy. I'm not sure how the history was, but my guess, people went through the hard way. They're not so smart as they want to pretend. So let us go do this. So it will be an exercise that we know the solution, but still. Okay, so this is what we want to solve. With all the Bessel functions. Because in the charge image method, where is the Bessel functions? Where did they vanish? I hope you all understand that if I have a plane here and a point up here, the symmetry is cylindrical because you have the z-axis, I put the origin on the plane and then the z-axis, and then you have phi rotation. What does this mean? We already know. L is going to be 0 because you have rotation in the phi. Okay, so we know some things. So what we're going to do is now we're going to solve this problem, and we're going to write V as the following. I'm going to guess, well, this is, in my opinion. Okay, so first of all, let us add here something. Here, what do I have in this domain? In z less than 0. Here it is the plus q. This is equal to 0. So, and the potential surface has v equals 0. What is this equation? This is Laplace equation. Why is it Laplace? Because there's no charge. There is image charge is not real. What is the solution of this down here? V equals 0. Why is that a solution? Because you have the Laplace equation, you have a boundary condition. The boundary condition is v equals 0. And if I plug here v equals 0, it's a solution. Laplace equation has a unique solution. We mentioned this. So v is equal to 0 everywhere. So the potential down here is trivial. absolutely trivial, and nothing happens. And this is actually what I mentioned before, that some charge will be accumulated here, just beneath, in order to get the potential zero, but it's more than that. The charge that we'll get here will be such that everywhere the potential down here will be zero. So yeah, but now we're going to focus on upstairs only. So we are going to write the upstairs. We're going to write this as x squared plus y squared plus z minus d squared plus v1. What am I doing here? Again, inside this, I have v equals 0. I'm saying we have to solve the Poisson equation. So I put here the potential that comes from a single charge, just the Coulomb potential. I know that the Laplacian of this part, what does it give you? A delta function, right? On the charge here. And this is the only charge that I have on top here. And then I'll have another V1. What does the V1 satisfy therefore? I hope it wasn't too fast. Maybe it's too late. What is the equation for V1 then? V1 equals 0. So again, plug this into the Laplace equation. This guy gives you the delta function of this charge Q. Then you are left with the Laplacian of V1, but already this charge was taken care of by this part of the potential. Then you are left with Laplace. Why is this useful? Because we are already experts in Laplace. We know how to solve Laplace. So I took the Poisson equation. Okay, there's only one charge, so it's a simple Poisson equation. And now I am back to Laplace. I'm very happy because we know how to solve Laplace. Okay, so now let us solve Laplace. And how do we solve Laplace? We go to this table. So what does, let us think about this a little bit. So again, we are solving in cylindrical coordinates using the table. And then immediately no phi dependence, L equals 0. It's again only for V1, it's not for the total potential. So now let us look in the z direction. What shall we choose? These signs or this sinh? Now corrected. We're going to choose these guys. Why are we going to choose these guys and not these guys? Because when you go up here in this way, up till infinity, what do the solutions have to do? They have to decay, they cannot oscillate. So we are going to choose sinh cos type of solutions, which means we are now on A. L is equal 0, YL, you have to throw away because it cannot diverge at any point here. So we are left with J0. Solution plus, this is the J0 solution, as you see in this table, is for the R component. That we have a cylindrical coordinate and we are going R outward. In the Z direction, we have this type of exponential functions. And this guy is vanished because L is equal to 0. Now, we need to think a bit. Will it be a sinh? Will it be a cosh? What will it be? And there is a difference in what we had before. There's a small difference. What is the difference? Now the system is infinite. All these Bessel functions with zeros and all these orthogonality relations will change now. The system is infinite, but let's look at the z direction. You have a sinh and the cosh. What will happen to the solution? Will it be...
It has to be a sinh.
It's not a sinh, and it's not a cosh. It's a linear combination of them where the decay is exponentially.
Could be tanh as well.
No, Tanch. Oh, I didn't think about that one. No, but because, I mean, these guys are simply exponentials that explode or decay, right? The sum of them. E to the minus kz, e to the plus kz, and the same with the cosh with a different sign between them. Out of all these terms, you can only have a decay. The solution, the potential cannot go to infinity at infinity because of physics, because far away the potential here is 0, you'll have an induced charge and the potential does not go to infinity. So it goes to 0, so it has to decay. So when I write here sinh and cosh, it's just, these are just functions, they are not wholly functions. What I mean here, you'll have a linear combination of them such that you'll have exponential decay. So it's the same thing, I mean, plus exponential decay in z direction when I go up. That's all. And that's it. We are, because we are trained in this equation, so in this table, so we are done. I mean, not done, but I wish we were done, but we are not done. But then we have V1, it's only V1, remember, is equal, and okay, here there's a new subtlety also, so I'm teaching you something new, AK, because there's no quantization, because the system is infinite, I cannot sum over solutions, I need to integrate over solutions. That's also quite common in quantum mechanics and many other places. And then I use this J0 K of R e to the minus kz. Just to repeat, this e to the minus kz, it comes from here. This guy here on the L equals 0, this goes away because it diverges, and you see the solution is very trivial. That's it. Well, it's trivial to write, that doesn't mean the integral is trivial, and we don't know what is AK. So what is AK? Now we need to think about it a little bit, and we need to use, what do we need to use? We need to use the boundary condition. So what is the boundary condition? Remember, this is only for V1. So the boundary condition is such that the potential, which is the sum V1 plus this solution, has to be 0 on the boundary. So what will give you this equals 0 when z is equal 0? Well, minus of this, that's all. So, and then I can write x squared plus y squared with cylindrical coordinates, that is r squared, right, the usual r squared. So on the boundary, v1 r z equals 0 is simply minus q r squared plus d squared square root 4 pi epsilon. I just took this, put z equals 0, and the minus sign, because all this together has to be 0, because v is equal 0 on this plane, z equals 0. So now I need to scratch my head at it. So we know, okay, so what do we know? We know that the integral from 0 to infinity dk ak g0 kr, I plug here z equals 0 because this is on the plane, the z equals 0 plane. This is equal to minus q 4 pi epsilon 0 r squared plus d squared. This is an equation for what? For this ak. From here we can determine ak. But now we need to go to our toolbox and get some tool. What is the tool that we need to use here? That is always the tricky part, maybe, or some part of the tricky part. Well, we have here only one special function, J0, so we might as well use orthogonality relation of this J0, but it's not the orthogonality relation I showed you before. There are no zeros here, there's nothing. There is a toolbox, there's one toolbox with the zeros, and then there's another equation. So, you know, you're like a plumber, you have this tool, that tool, you take it out, and each time you need to use a different tool. It's not easy. That's why you need a lot of practice to solve these things. And the orthogonality relation is the orthogonality relation of the Bessel functions, but now in the continuum. Okay, so what is that orthogonality relation? just write it down. It's taken from the textbook. It's the integral from 0 to infinity, J0 KR J0 QR R dr. Now it's a delta function. Instead of a delta of Kronecker, delta mn we had before, now it's a delta function in one dimension, but a delta function divided by q. I'm not proving this, but I'm using this. Bochman should prove this. I guess he also didn't prove that. So this is a kind of known equation that I'm going to use. It's, by the way, you can ask, okay, here I did it for 0. It's valid for any alpha, I think, bigger than minus half or something like that. There's a more general equation similar to this one. So now we can find this AK. So I think now we are going to say goodbye to our beautiful table, because now I'm not going to use it anymore. So let us do this a little bit slowly, but it's not difficult to filter out A with this equation. So let us write it, okay, let us write it so I won't make silly mistakes. Integral AK, what do we have here? Dk J0 KR dk. This is, I wrote dk twice. This is this one. This is equal minus q 4 pi epsilon 0. How do I want to write it? I want to write it, yeah, with it r. R squared plus d squared. This was simply minus the potential on the plane created by the real charge. Okay, so this is this thing, then I multiply this by J0 QR times R, and then plus integrate. So then I'll have here integral from 0 to infinity dk AK J0 KR J0 QR multiplied by R. This is because of this. And dr. Now all this junk, this gives you delta q, this delta function, q minus k divided by q. Then I need to integrate by k, so I'll get a q divided by q. This q down here will eventually pop out. But this, on the other hand, is equal to this integral on the other side. Q 4 pi epsilon 0, integral from 0 to infinity, r squared plus d squared, half, famous half from Coulomb's law, integral over J0 KR r dr. This comes from here, the same that we had here. Now we have this solution, and would you believe it or not, but one can solve this integral. How do we know we can solve the integral? Well, we know that there is an image method, so most likely people can solve this integral. Okay, this is not a proof, but this is the reality. So what we get is, okay, this is eventually, oh sorry, this is Q. We get this, and all this integral is e to the minus q, q as units, 1 over square, so what will come with it? Of course d times divided by q. Okay, we can add here 4 pi epsilon 0. So this q here and this q on the other side here will vanish, and I got AK. So then I can plug this AK back, and I have the, it looks like the solution for V1. It's a function of R, the distance, and Z. How far you are. Of course, when you go very far away, the influence of these things has to diminish in some way. And then this is equal to minus Q 4 pi epsilon 0. This is simply the A that I'm plugging in here. That's it. And then I have the integral J0 KR e to the minus, I'm writing AK, not A cube. Here I have K Z plus D. Plus D because AK is minus QD, so here is KD. KZ is this one. And this is the solution. Now, what is the solution? What is this potential? What is the integral? You know the image method, so you know the solution. What is this V1? I solved the integral, or someone solved the integral 200 years ago. One R squared Z, and maybe we should emphasize this. Here we have a plus D squared half. What is this? What is this V1? Now we can be over chocham and very clever. What is this V1? What is this V1? Remember, here I had the minus. Why did I add the minus? I put the plus charge on top here. If the charge would be on bottom, I would have here a plus. This is this thing. This is the image. This is the image which you get if you put another charge on minus. Now you go to high school and you are a very clever guy. Here I'm going to solve you a very complicated problem very easily. I'll take a plane, potential is 0, put one charge on side. Now let's put another charge down here. Potential, what would be the potential on the surface? Because they are the same size and the same distance from the plane. One with the plus, one with the minus. The potential is 0 on the surface. That's my boundary condition. Then we are solving the Laplace, the Poisson equation on top. So the other charge is not real, it's the image. So you take the Laplacian and then you get a charge, which is the delta function, which is your charge, and then you are done. So once you get this solution, you understand what is physics. So you can look at it in two ways. You can say all this math, you don't need it, but you should also ask yourself, is that actually true? Because I mean, most problems you cannot do all these tricks. You cannot solve these integrals. So this is exactly the image method, but now we proved it kind of rigorously, going through using our famous table. At the end of the day, there's no Bessel functions and nothing of that sort because students in high school don't know what's a Bessel function, but you can still solve it. So to summarize, effectively we found an image method, which you know. I can replace the problem with a plus Q up here. Here is the plane. Here V is equal to 0 and a minus Q here. The distance is D and the distance up here is also D. That is why it's called the image method. This is not a real charge. It gives you, again, I repeat myself, it gives you the potential on the surface 0 because the plus and the minus cancel out. The potentials add up and then they cancel. And you solve the Poisson equation because the real charge is, again, giving you the Coulomb solution, which the Laplacian will give you a delta function, which is correct, with the boundary condition that you imposed, and then you are done because this is the solution. So, in other words, the image method, you practically guess the solution and you are done. And this is what you know already, which is fine, of course. This is the beautiful thing. So in physics, many times you go through a lot of ugly mathematics, and eventually you find something which is simple. That means usually that you can have a nice, simple physical explanation. That's the image method. Okay, so we are more or less done here. We can ask now some questions. So we are interested only on z equals 0, but we can imagine this thing here and here plus, and here a minus. And now we can forget about the plane, but only look on top, not on the bottom, because down here the potential is 0. And then we can ask, how does the field behave? So how does the field behave? So if you have a plus and a minus, that means what is this system? Essentially, it's like a dipole, actually. Okay, you know more or less, you know how this will behave. The field lines will go, these are the electric field lines, something like that, with the spherical symmetry. Because they start at the plus and then they go to the minus, as I taught you before, and then close by here, the density of these lines is very high, because close to the charge, the field is very big. That's why this is the meaning of this high density. And then when you go out, it will be more and more spread, because the electric field now is going to be less and less. And then we can say, what is the charge here? What is the charge here? How do you know what is the charge on the surface? The real charge that the experimentalists can measure in principle. So how do you get the charge? You build here a small Gauss box. The electric field underneath is 0. The electric field on top, can we calculate it? Yes, because we have the two charges, so we can calculate it. And then I can calculate the electric field here. And the electric field, then with this small Gauss box, I use the fluxes, usual Gauss box, and then I get the density, which is what? Simply the derivative of the potential up here, which is the electric field. That's the sigma, the charge density. So if you do this exercise, because we know the charges, we know the V of dz at z equals 0. So the charge density, this is again the charge density per unit area, because the plane is in two-dimensional, that's charge divided by meter squared. We use this potential, and then we get minus d, sorry, qd, capital Q. The bigger is the real charge on top, the more charge density you have. This is obvious. If you have a big charge up here, many coulombs, okay, the induced charge on the surface will be higher, so it's linear in Q, that's obvious. And then you have here, like this, x squared plus y squared, which is r, d squared, 3/2. So what does it mean? It means that the charge density, when you go out in R, this is R, is simply decaying according to this law. Now you can ask what, and it's minus sign because the charge up here was plus. If I integrate this thing over all space, what will I get? You will get minus Q. If I integrate this, so what does it mean? You have charge density. Because of this charge plus attracts minus charges, but it cannot attract it too far, so it decays in space when you go out in R with azimuthal symmetry. And how much charge does it induce here? Minus Q. Is this a contradiction to conservation of charge because the total plane is neutral? What does it mean actually? The plane, there are charges, but they go to infinity in this idealized world, such that the total charge of this plane is still infinity, and then here you have minus Q. it doesn't mean that this has to be, this is still neutral, but the other charges are pushed to infinity. So this is the physics of this thing, and now we can ask a more general question. First of all, can we make this more general? So in the homework you'll have the similar problem, but now instead of a plane, you have a sphere with one charge. You can still do the image method. This is another example. But now we want to go to more general, maybe not being able to solve total amount of problems, and we want to formulate this. We want to formulate the image method and actually extend it. I mean, the image method, obviously it can work when you have very beautiful symmetries. Eventually, real problems don't have these symmetries. So we will find a more general method, which is a bit more abstract, which means we cannot really solve things, but we can solve it semi-numerically, whatever. And this is called the green function method, which is related very strongly to this image method in some cases. So the green function method. I'm not going to teach you all the green functions. I'm going to teach you the green function method for the Dirichlet boundary condition, where the potential is zero on some surface. And again, we are going to start with something trivial. What is the idea? So the green function. Let us start with what you know from high school. So it doesn't give you any new information, but it will, what I'm going to tell you now will help us define a more general concept, starting with something very well known. So let us discuss the simplest case, going back to Coulomb's law. Coulomb's law, okay, it's trivial. Let's make a trivial thing. What do you do in university? You make a trivial thing, you make it complicated. At the beginning you say, why did I come to university? The reason why we make it slightly more complicated is then we can generalize it further and further and further to more interesting behavior. So it's not that I'm a really nasty guy, but still, it will at the beginning sound a bit maybe idiotic. So I have two coordinates, r and r prime. And on this point I have a charge q. And then I have this distance, r star. This point r is where you have some observer, I'm not going to write in some devil here, he's sitting here and he's measuring the potential, we want to know the potential, and we know the solution. We know that at r, at point r, if you want, this is v, x, y, z, right, at some point. This is very simple. It's simply formally 4 pi epsilon q over r star. R star is the distance here between the source, and we also know that rho is simply a delta function. Okay, this might not be in high school, but and it's on r prime. So notice here that I have two coordinate system. The green function depends on these r and r prime. So the green function is a function of 6 coordinates. Therefore, it's not so. It's something to get used to. What else do we know? And we already said this already. We know that the Laplacian of essentially the Coulomb potential gives you a delta function, and I'll formulate it slightly differently, without the coefficients, but with the 4 pi r minus r prime. So this Laplacian is with respect to r. Okay, this is the Laplacian that the observable is on r, the charge is on r prime. This is what? You know this. This is a delta function. The minus is related to this minus that we have here. Maybe you don't see this immediately. R minus r prime. Now, what I'm going to call as a green function in this trivial problem is this is the green function for this problem. So there are many green functions depending on boundary condition 1, boundary condition 2, boundary condition 3. There's infinite number of green functions for different types of problems. Now I'm just going to define the green function for what problem? When we have one charge and then there is no boundary condition except at infinity. I'm just saying the potential at infinity is 0. That's the simplest case that you learn in high school. In high school. So this is what I called here G, I don't know why, 1 R prime. It's a function of both R and R prime. Why do I care about this function? In this problem and in generality, this green function, I can do now something trivial. I can write that V, let's call it now x, y, z, is equal to integral over the whole volume of the system where the charges exist. Okay, so now I consider okay, so this is an integral over all space. I can write it like this. Rho of R prime, GR R prime over epsilon 0 dV. V is integration over all space in this case. Why do I say this? Well, it's trivial. It's really, really trivial because this is given integration over the volume, rho of R prime. I just copy this thing, 4 pi epsilon 0. This is familiar from you from Coulomb's law. This is this 4 pi. R minus R prime dr. So what did I do up to now? Absolutely nothing. I didn't do anything, right? Because what does this say? This was for the example, but this is a delta function. This is simply the Coulomb potential. So I call this a green function. It's just renaming. So why should I bother with this? Because this gives you the scheme and why people care about green functions. Let us think about this. Let's say you didn't have one charge, but you had many charges. Would this equation still be valid? That's called the superposition principle. I could have any charge here. This is what we learned already. Any charge here. So what is the idea of green functions in one idea of green functions? Very simple. We don't want to solve problem 1 for density 1. We don't want to solve problem 2 for density 2. We just find the green function, and then in an experimental situation, you give me what is rho, and then I'll do the integral. The integral, it's not so easy, but it's a different problem. You solve this integral numerically. I just want the green function. And in this case, we did it already. Here is the green function. So the idea is simple again. I repeat myself. We want to find a function called the green function that solves not one problem, but essentially if you know it, then with another integral you solve everything. But this is trivial. We didn't do anything because this is just Coulomb law. Now what will I do to make it more interesting? I would apply boundary conditions which are not V, the potential is 0 at infinity, but we'll put it on some surface. Then the green function will not be so silly like you learned in high school. It will be something else, something more complicated, because you add the boundary condition. And then it will become interesting. But still, you will have a green function that will solve you any problem you want if you know it for a given surface. So you have a surface. On this surface, let's say the potential is 0. Then you can put some charges on this in the shape of a moon, as charges on the shape of the sun. It doesn't matter. If I know the green function and I am ready to do this integral, I solve these two problems, even though they are very different, and even if the physics is very different. But the green function is the same for these two problems. That is the motivation for this thing. So let us start with the problem that we already know. What is the green function? I'll just formulate it. We are starting rather slowly through example. So the example that we know is just the example that we solved just now with the image method, and we're going to find the we'll make it a slightly more. So now I want to find the green function. Again, a green function depends on the boundary condition. I have this infinite plane. And now I have charge density up here, rho. From physics point of view, we can understand what is the solution. If I have some charge density up here, what do I need to do? I need to put a charge density for each charge here minus here, same distance, but the opposite object. And that will give you the condition of potential zero. Okay, it can be very hard because this is an amoeba or something. So the integrals can be very difficult, but essentially that's the physics and that's the image method. Instead of doing it for one charge, we're doing it here for many charges. So we're not doing anything really too complicated. So now I just make the claim. What is the claim? What is the green function? And soon we'll define it in this problem. It depends again on 6 coordinates, unfortunately. This is this, forget about the 1 over 4 pi. It's like before, on this 4 pi epsilon. It's just a convention, it's not so universal. And then let us write down this green function in this problem. It is x prime minus x squared, y minus y prime squared. Pretty awful thing. All this square root. Minus, this is the image. Here I wrote it like that, okay. And what we'll have here, that's the only difference. Plus, that's the only, if it would be minus, it would be 0, right? So I claim this is the green function solution, and then let us understand why this is the green function and what exactly this means for this specific problem. So what does it mean? The claim is the following. Let us just say the claim. The claim is that Vx and y and z, this is again for z greater than 0, in the underneath here there's no charges, it's only above, is equal to the integral over the upper plane, but you can integrate also the lower plane if you want, the charge density. So the charge density is in 3 dimensions. So here I have some amoeba with charge on it, multiplied by this green function that I just now gave it to you. Epsilon 0. This lesson I call it dv. In Griffith is d tau. The integration is over, maybe you want a Chupchik, over the r prime. So the solution depends on r, and this is the solution. So again, repeating what I said, you give me rho, I know this g, I'll give you v. And the key part is this one. And again, this one is just saying, what does it actually say? Forget about the units, about the q, the charge comes into the rho. But this is essentially like a potential at one point up here. And this is the potential of its image charge down here, like we had before. But why is this a solution? Okay, can we easily see this? The answer is, if you look at it for 2 minutes, and I know it's late, it's obvious that this is the solution. Why is it obvious? What do I need to show? I need to show that this solution satisfies the Poisson equation, right? And I need to show that it satisfies the boundary condition, and then I'm done. Why does it satisfy the Poisson equation? I'm going to use words, but I'm not going to use math because it's so obvious when you look at it enough. So it satisfies Poisson. But why does it satisfy Poisson? Why does it satisfy Poisson? And what is the equation for G? That will be actually an equation general. What is the Laplacian of G? So I take the Laplacian here. Laplacian of V should be what? It should be give you the charge density, right? So I'm plugging here this Laplacian. It acts on R. Where is R? It's not here, but it's here. So what is the Laplacian of G? What should it be? It has to be a delta function. Okay, it has to be, but is it? Look what we have here. This is what we said before. This is why I mentioned here these simple problems. When I take the Laplacian of this guy, you get a delta function, but now where is the delta function? On x prime, on y prime and z prime. This delta function gives you another delta function, but where is it? It's located underneath because of the plus z here. So it's not going to be important. So here, when I take the Laplacian, I'll get a delta function. Soon we'll write it explicitly out. But if you have this delta function, and then you integrate, it's not a delta function, it's minus a delta function. You see this minus. So here I have this delta function, and then I integrate rho of r over a delta function, and then I get rho of r divided by epsilon 0 with a minus sign. That is the Poisson equation. Okay? Satisfies Poisson equation. Gives you delta function. And it satisfies the boundary conditions. Why does it satisfy the boundary condition? This is very easy to understand because the boundary condition is on z equal 0. That's this plane. If z is equal 0, minus z prime squared is the same as plus z prime is the same. So G, R, is a complicated thing. When I take z equals 0, is equal 0. So if I take r equals 0, z equals 0, then this guy is 0. Then if this is 0, then the solution, the potential is 0. So the boundary condition now, what did I do? I shifted it from the potential to the g. But immediately if it's 0, at least for the Dirichlet boundary condition, it's 0 here, so it's 0 here. And you are done. Okay, so now if you really want, let's see this. And again, to understand that why this is a delta function, it's the same like we had here. It's not very difficult. So maybe I will not write it down, but because I think it's a trivial, it's exactly the same that we had here. And again, the domain of the integration is z greater than 0. You don't need to worry about the other delta function. The other delta function has a meaning. That's the image method. That's the image that you have here. That's why for these problems, the green function method and the image method are very similar. I think you agree. Now we need to ask, can we go also to more complicated methods? So you can solve all kinds of problems. For example, I can now solve easily, let's say I have a charge density and here V equals 0. I can find this quite easily because I can do the integral with these things. There are all kinds of problems, but because we are a bit late, I want to now, instead of doing that, some special example, I want to now formulate this a little bit more. So here I said this is G, here I said this is G. Now you have a headache because, okay, you know 2 G's in the world, you know it for a sphere. And now let's say, more generally, how do we find G? What is G for a general boundary condition? Of course, now it's going to be more abstract, but we can find G. I'll do it. Hopefully, I know that you are tired, but so what? Also, I'm tired. So let us look at this. what is the general formulation of green functions? Again, this is not the most general, it's only for Dirichlet boundary conditions. So I have a general solution, for example, v equals 0 and some rho of r up here, or simply v equals 0 and some charge density inside. And this amoeba can be anything, so if it's an amoeba, we cannot solve it exactly. There's no exact solution, there's no magic, but we can formulate it. So what is the definition? The claims. What are the claims on the green function? The first claim on the green function is the following, that, and you saw it, but now I'm generalizing it, that this thing will happen. This is a delta function in 3 dimensions. This is, if you want, the definition in general of the green function. Why this happens, we'll soon see, because if this happens, then you have your delta function, then you take out rho, you integrate, you get the solution of the Poisson equation. I hope you follow. So this is a green function definition. It's inside, the definition is inside some boundary domain. So the boundary domain here is on top, and I'm closing the domain at plus infinity. You have v on the boundary equals 0. Again, this is called Dirichlet. Then you can have the derivative. That's my man. You can have v equal constant. You can have many things. I'm not going to discuss all the options. For this boundary condition, the second condition, g r prime, is equal 0, like the potential. We also had it before, you see. We said this minus this on the plane was 0. Now I'm doing the same thing, but more generally. So it's this on boundary. Sometimes it's called mu. So this is the boundary. This plane is mu. This one is, this surface is mu. So the same boundary conditions for v and for g. So what does v satisfy? V satisfies the Poisson equation. With what? With the appropriate boundary conditions, which are 0 on the surface. So this is not enough. This is the physical charges. And what we want to do is relate this rho to this v using this g. We are not saying what is rho, we are saying give me g. To give you g, you need to solve this equation. Easier said than done, but in principle you need to solve this. So what is the claim? Just the claim. And we saw it in the two trivial examples. The general claim is that v of r somewhere in space is 1 over epsilon 0, that's a matter of definition, over the volume, that's including the domain, like up here, or in this, all this junk. Of course, if you have a charge inside and the boundary is defined far away, actually the real integral can be over the charge only, because here inside there's no charge, right? So it's actually where the charge is existing. G r prime rho of r prime. D v prime. So you integrate over the r coordinates. That's the claim. And because it's very general, the proof is trivial. Again, take Laplacian. Take the Laplacian. The Laplacian of g, by definition, is this delta function. integrate over R. You are integrating what will get minus rho over epsilon. I'm happy because that is the solution of the Poisson equation. I didn't do much, but I'm just saying there exists a function g for every charge density you wish. You should find it by solving this equation, which has no clue about the charge. It doesn't care about the charge. That's the strength of this method. Secondly, boundary conditions are valid. Again, why? Because g on the boundary is 0, and then that's the same boundary as v. That's it. Okay, so this is the solution, formal solution. Very doesn't mean that in practice you can do too much with this. Now the question, what is this g? Well, I already said we cannot find g in general, but we can reduce it to a simpler problem, and that's an eigenfunction problem. So eigenfunction problems, not necessarily easy, are still easier maybe from solving this equation at the very beginning. So the claim is we have some basis, some general basis, whatever it is. The basis will be defined by the boundary condition. We have here some eigenfunction, and this is the Laplacian, and this is equal to lambda n u n r. So these are eigenfunctions. These are eigenvalues. The solutions u satisfy the boundary condition. Whatever the boundary is, they satisfy the same boundary condition. The claim is that if I know these eigenfunctions and eigenvalues, I know the green function. So this is a method where you solve the eigenvalue problem, which is simpler, to get the eigenvalue problem. So to do this, let us do a little bit of math, without proving all the math. Just so you can get a feeling where does it come from. It comes from the fact that these functions in general, so think about them, the simplest case would be in a rectangle or something like that. That would be sine functions and cosine functions. But in general, they will have a completeness relation. So they form a complete basis. And you can expand any function with these set of functions. So it's like a series, like Fourier series, which is in a special sine and cosine base, but now in some abstract functions that sometimes you know and sometimes you don't know. So maybe you know this equation and maybe you know this, but mathematicians have proven that in general, by the way, this n, I write it as some index. What is this? It's a quantum number, but it can be 3. And usually it's three indexes because we work in 3 dimensions. So it's actually a vector, but I put it in one number for now. So yeah, because the Laplace in 1 dimension this will be a number. In 3 dimensions there are 3 numbers, in principle. But again, for simplicity, let's write it as a integer. So what do we know for math? We know for math that UNR, UMR, dr is equal, sorry, we want to write it like this. What it means is there is a freedom in U. This is actually a one-dimensional notation, but there is a freedom in the choice of U, but we chose them such that they are normalized. And this is always legitimate because the equation here is linear, and the math gives you automatically that they are orthogonal. And again, you know this, I think, from other courses. I'm not proving this. So you say you form orthogonality, and that's why you have this type of uncertainty relation. And in principle, this is not a delta function of two variables, but vector m, which means all the indexes have to be the same. I'm not going to prove, but assume this means that maybe you saw this before, that the delta function in 3 dimensions can be written as a as this function. If we have time, I'll prove it to you. It's not so complicated. Did you see this type of identity with Rochman? Yes. Good. How do you prove it? I mean, the way you prove it is you have this delta function and you say, let us expand it as a function of r with some coefficients. And then you use orthogonality to get these coefficients here. So this is called a completeness relation. Again, if you want, come to me after the class. I'll show you how to prove this in 2 lines. I'm not going to do this. So the idea is, what is the green function? Let us write the green function, some function. We can always write as a linear combination, and again, I'm using the fact that these U's, they form a complete set. So I can write it as some linear combination. CNR prime and U and R. This is an expansion with some numbers which depend on R, and this is a complete basis. Of course, maybe mathematicians don't like it because of these delta functions, but we assume this is valid. Now we have these CNs. But, okay, what do we know about G? We know that this G is equal to delta R minus R prime. This is the definition.
I think you're missing normalization in the first equation.
Here?
Yes.
Why?
He said it's orthogonality, not orthonormality.
No, I'm defining the functions U as being also normal.
Oh, okay.
And I said that I can always normalize them because this equation is linear, so I choose them such that they are normalized. This is very standard, because I want to do that. So, okay, so I can just use this equation. Let's do this. And then let's apply this to some Cn R prime Un R prime. Sorry, Un R. This is this one. But what is the Laplacian on Un? That is simply given by this guy here. This is equal to minus sum over n Cn R prime lambda Un R, and all this is a delta function. But the delta function from this identity is the sum over Un R prime. So this guy, here's the lambda n, and this guy are the same. We can use again orthogonality. I can multiply, integrate, but you can immediately see it. And now I identified what is this Cn. You see all this Cn R, it has to be valid for all R. This guy is the same as this guy. So I know what is Cn. Cn is simply this UNR divided by lambda n. Now I'm formally, I'm done. Why? Okay, so let us write it down. Cn R prime is this Un with a minus. There's a minus. Here's the minus. Un R prime lambda n. Now all I need to do is just plug it in here, and we have the green function. So the green function is the green function is the sum over n u n r prime u n r over this lambda n.
What would you do if you have eigenvalue of 0?
That's a good question, but in these problems, think about it because it's late. Let's say a particle in a box, so the ground state energy is positive. So there's no zero eigenvalue here. We are thinking about a finite domain. And in a finite domain, the spectrum is discrete. There's no continuum, so you don't reach the zero. If you have a continuum, and you have a zero boundary condition, a zero eigenvalue, which will not be in a finite domain, it's not part of this. Yeah, but that's a good line. But I assume here lambda n is bigger than 0. So here we are done. So we got this equation, and now in the 5 minutes remaining, let us do one example. The question is, what is the simplest example that we can do? So what I want to do, so generally speaking, this is in 3 dimension, this is complicated. Let us do it in 2 dimension. Then we will also learn some new physics. There's no, the basic question, what is the potential, if we would live in 2 dimension, what would be the Coulomb potential? You know, what would it be? It's going to be logarithmic. Who says? You heard it somewhere, but this is, yeah, this is correct. Rochman told you.
Yes, it wasn't in his exam.
It was in the exam, even better. So we are going to show this through an example, and for that we're going to go down to dimension 2. But it's not only because I like dimension 2 versus 3, it's also because I don't like to, the green function is so complicated, I prefer to write it in 2 dimensions than in 3. Because actually, when you write it in 2 dimensions, it's going to be kind of easy. And then to extend it to 3 dimensions, you'll immediately understand what it should be in 3 dimensions. So the example I want to take this is the simplest example I could imagine, is a square. This is 0a, this is 0a, this is xy. Now if you don't like 2 dimensions because you want to work in 3 dimensions, think about this as a box. So also the z is in this dimension. So what are we actually solving here? Because we are saying on this the potential is 0, and inside there is some charge density, and different problems have different charge density, but I'm looking for the green function only, and then I need to integrate. I'm not going to integrate, I'm just looking for the green function, which is given by these equations. So what is the green function? So now, what is the Laplacian? First of all, this is, I choose here the simplest Cartesian coordinate, so what is the Laplacian? So I have here, oh, this is bad. What is the Laplacian? Laplacian is simply d over dx squared plus d over dy squared. And if you want, I'll have here also z squared if you want to work in 3 dimensions. We have these functions u. I told you that there are 2 quantum numbers. Now, y2, because it's 2 dimensions, 3 if we have 3 dimensions. This is a function of x, y. I just took the minus to the sign here. Lambda nx and y, ux, nx and y. What are the solutions here that satisfy the boundary conditions? Trivial solutions. What are they? Sines. Why sines? Well, let's say sine x, this is the x. Sine at x equals 0 is 0, and sine at x equals a well, we'll quantize through this n. This is the quantization rule, like a particle in a box. So in quantum mechanics. So the solution is trivial. So these are sign solutions. The quantization of nx and ny, these are numbers, 1, 2, 3. They, again, how do they appear? Because of 0 on the boundary. What is lambda? How does it go with nx and ny? Like squares. Like, because why? Because you have the second derivative of a sign, it will give you nx squared plus ny squared. Like what problem in quantum mechanics? Like a free particle, or particle in a box, k squared. It's like energy in classical mechanics, E equal p squared over m. It's the same thing, but in quantum mechanics it's quantized. So this will give you, this lambda is nx squared plus ny squared. And there is a coefficient here that depends on the size of the box, on this A. You understand how to solve this in principle? I don't think I need to solve this. Now I have this magical formula, and then I can write down what is G. After I normalize, there is some pain on the way. And if I didn't make any mistake, then G x prime, okay, G x y. So G again is a function in general of 6 coordinates in 3 dimensions and 4 coordinates in 2 dimensions. And because I'm lazy, I'm doing it in 2 dimensions. Now I have the eigenvalues, these sign functions, I have this, and I can plug it in with the normalization. I get here, this is 4 sum over nx and ny. This is the meaning of this sum. I told you this is a vector of. And then I have here this lovely equation, which makes you hate physics. Okay, so first of all, I'm going to take a equal 1, because I have too many parameters. So nx pi x, so it means that when x is equal to y, which a, which is on the boundary, this function is 0. That's the boundary condition, right? Because I just put it. And then I have sine ny pi y. What else do I have? The same function, but with x prime and y prime. The indexes are summation indexes, so I'm not changing them. Pi. Pi comes from this quantization, never mind the indexes, and here I have nx squared plus ny squared. This is from lambda. This comes from normalization. These are u's, eigenvalues, eigenfunctions. So again, eigenfunction in 2 dimensions multiplied by eigenfunction, because I have r prime and r. Eigenenergies go like high school energy, k squared, it's the same thing, p squared. Free particle, it's the same thing. And you have this beautiful equation, but it's really horrible and most likely you hate it. So now the question is, what do you do with this? So this function g is too complicated, because I have x, y, and if I add x, y, z, 6 coordinates, it's too much, right? And it's too late, you cannot understand what it means. So let us make it simple. What is simple? How do I simplify this? I will use the rho of r, let's the simplest case, and that will make a physical meaning for the g. If rho of r is a delta function, then this integral is trivial, and v up to epsilon 0 is equal g. So what does this mean? What is the physical problem I have in mind? You have a box, this box, and I put a charge, one charge, just to reduce the problem to the bare essentials. Now where should I put the charge? Well, let's put it in the middle because that's the simplest problem. So G has a meaning of a potential for a single source charge. That's the physics of it, because of this, because I put here a delta function. And now this G symbolizes a potential in this problem. Now still, I have a problem. This G now does not depend on x prime and y prime anymore. What do I mean by that? I need to plug in here x prime and y prime in the middle of this object here, because I integrate. This is what I mean. I mean, I'm going to look at the green function at this point, where with respect to x prime and y prime, and this means physically that we have this boundary condition 0 with a charge here in the middle. Is that clear? By this integration that I have here. And then I can represent at least the potential, which is the same as the green function, at a specific point r prime. Now, of course, I can move this charge anywhere. That's the beauty of this green function. And find out all solutions by integrating this monster over all kinds of delta functions, or not delta functions, whatever you want. I can do that, so that's why it's so powerful. So what will happen in this case? I put it in the middle, and then I go along this axis. How will the solution look like? Anyone has an idea? It's what you expect. So this will be v of x, y equal 1/2 for the system, the charge in the middle. It looks like something like that. I cut it off here because it actually diverges. First of all, it's very different than the Poisson equation. The maximum now here is in the middle, but that is trivial because we have a charge now. It's not like Poisson. So the maximum is inside. Where is the maximum? Close to this charge. You can use this horrible sum and look at the behavior at this vicinity. How does it diverge here? Here, the boundary, this is 1, so sorry. This is 1, this is 0, this is 0. So at the boundary it's 0, but this is trivial because this is the boundary condition. You can look at the solution in this vicinity, and this was given apparently by Rochman. And you can take this expression, and you just plug here 1/2 and 1/2, and then you expand y and x in the vicinity of this point, not far from this point, at the vicinity, and that will give you a logarithmic thing. I guess Rochman did it in an infinite system. So here the potential diverges, but logarithmic. Diverges logarithmically. If I do the same thing in 3 dimensions, nx squared plus ny plus nz, and here I have 3 functions, it will diverge how? Exactly like in Coulomb's law, the usual Coulomb law. So you can play with this with ChatGPT, and you can find this thing, and to find this divergence you need to expand, and then you need to turn this into an integral. There's a lot of math going on, but I just said that in 2 dimensions the charge will become to a logarithmic divergence instead of a 1/r divergence. And this solution you can solve again. You can use it for any charge density inside this thing. How come I was able to solve it? The boundary condition was rectangle, so I could find this mu, these 2 functions.